Now we're inside the VCOs, and I got another defect unit for scraps. So that is why it is now possible to super dig into how stuff is made. This is the Vco voltage. It is directly connected to this capacitor. I think it's a tantalum. So now see, there is a 2K2, and then here's a capacitor to ground. I believe between these 2 points we got a diode, and then we've got a resistor here to one end of the transistor. So there's a transistor in here and a diode, and one more magic thing. So you see those 2 golden pins? That will be the oscillator transistor, and this is of course the resonant circuit for the oscillator. The output of the oscillator goes to a buffer transistor that is down here, and then of course it's buffered some more, right? So this is the interesting part, and let's look at the other side. See, here we go. Here and here are 2 connections that goes straight through. Let me bend this a little bit away so we can see this point is connected to ground, and then there's a tantalum, and this point is connected to this, and then there's an inductor. So this is the heater voltage that goes to the heated oscillator. And here is the thing. I took apart the other one of them. See, here is the heater. Inside the heater there was a hole in the middle where the transistor was sticking in, so that the heater is heating up both the transistor and the diode. That is a variable capacitor diode for the oscillator, and this is of course how it works. The oscillation frequency is controlled by the reverse voltage of this diode. So that is built into one unit from Texas Instruments. I can't really make up what it says. AT board, I don't know what that is. If anybody knows that, yeah, I have ever seen anything like this before. Oh, there's even a number here, 5ST2-2 maybe. And it was, I believe it was screwed in there, see? Is this a custom part or is it something you buy? I'm of course going to see how this works. But I believe the heater is made of this PTC, temperature stabilizing material. I don't know if I can make this real sharp, but this, yeah, I'm sorry, but I had to break this to figure out what it was, because in the beginning I thought this was a coil, but no, this is the heater. So I'm actually going to power this up, because this one is not broken, so I can power it up and play with it. So here we go. I am powering up the heater, and that is clearly a heater. It does exactly what I expected. Now I let it stabilize a little bit, and it goes to 1.2 watts. And let's see what happens if I turn it off just for a little while, and then it's going to cool down, of course, and we're gonna see what happens, right? See? So now the power just go down and down and down until it stabilizes. So that is clearly a temperature controlled PTC heater. Fantastic and genius design. So here is the other unit. Here in the bottom we can actually read the 5ST2-2 P4A. What a tie board. I don't know what that is, and then USA or something like that, right? But anyway, when you pull this apart, it was full of grease. So this is of course thermal conductive grease, some white transparent sticky snotty, and then here we see the diode and the transistor. Really cute. Maybe we can read the number on the transistor. Yeah, så det var sjovt. Also, I found out exactly what this is in Avionics. As you can see, it says impedance 500 ohms, time delay 2.0 microseconds. So this is of course just a delay line. And the other one is looking a little bit different. Maybe it's a newer model or something, but it's the same TD2. So those I'm gonna keep. They're pretty cool. Also, I saved from this completely dead unit a really nice capacitor. I like that one. And I think this is the King Kong score of this unit. Look at this variable attenuator, input and output. Wow, so they even somebody signed it. I can't read what that is. This name is BRARTHERS or something. Serial numbers and everything. This is of course something I'm going to measure how it works, and of course we're going to open it. Don't you want to see what is inside? But first we're going to measure it, right? And then I found all those directional couplers. They're exactly the same. And they are 6 dB, yeah, 6 dB coupling, and they're quite narrow band, but I think this is just a specification where they're the best. So they bought these for that frequency range, and inside this frequency range, this is going to be 6.0, right? This is of course something we're going to measure. Then I found the linear RF detectors. Detector output. How exactly is this working and what is in here? I don't know. Ooh, you see this city here, Palo Alto, California? Funny enough, this is also where HP came from, right? And here is a really funny device. Again, one of those detectors. But then again, what is that? And how do we find out what's in here? We're gonna open this, right? This one I found no name on it. Maybe it's a custom thing, but I will have to see what is in here. First I'm going to measure with an ohm meter. Oh yeah, and some really nice low pass filters. Those I really don't want to open because they will break. And if you ever find something like this, please don't open them. because they consist of a step impedance filter in here. So this will be the low pass filters. Most likely. I am of course going to measure these and see what they can do. But first we need to clean up. I'm testing the attenuator. This is a really cute variable attenuator. And this is a full span, 3.2 gigahertz. See? I'll just crank it out a little bit. And it is really, really flat. I am very, very impressed. So this unit was a 1 gigahertz unit, and we got 3 gigahertz component in here. That is just a King Kong score. Definitely. Look at that. Whoa. I can't wait to see what's in there. Oh yeah, I forgot to show you guys this really nice filter. Oh, this is super heavy. So this, of course, we're gonna go sweep as well. That is probably the weirdest filter. What? Look at that. Let's go and get a marker. Hello, marker. Let's of course go down to the frequency range. Oh, here. So this is the 1 gigahertz range, and there's nothing going through here. That is weird. So what is the whole idea about this? So this filter is really good for anything below 200 megahertz. So this is not connected to the output. This is probably the 100 megahertz. Aha, so this is in contact with the 100 megahertz signals, not the output. That is weird. I think I'm gonna go and try and reverse this and see what happens. Of course, it was me who was absolutely stupid. Look at this, output and input. So the input must be connected to the tracking generator. Alright, now it is connected correctly. So what this is of course an isolator. So it contains an isolating circuit. So anything from like 900 and all the way up to 1.3 goes straight through, but in the right direction. And this is of course the pass band where this unit is designed and where it works. And then in this band, if you put in anything in reverse, you'll get if you put in stuff into the output, what I did, that means it goes into the loads. Got another load, and we got another load. So this is probably a double isolator. So there will be 2 of them in here. And they consist of a magnetic circuit and some inductors and stuff. It's ferrite and funny stuff. So yeah, isolator. Let's look at the low pass filters. This will be the shortest one. And again, no big surprise. 1.3 gigahertz for minus 3 dB. So this is of course a low pass filter. And the big one is just also a low pass filter. It's very close to the same specifications. I think it is actually a lot more steep here. A little bit lower frequency for the minus 3 dB point. And because it's longer, it also contains some resonance stuff. If you use equipment with a lot higher frequency range, you will see something happens and then yep, it goes up again. And this is the directional coupler. This is the input to the output. And so this is the coupling port, which is not connected. If I put a load there or not, it's almost not affecting the input and output here because this one is 6 dB coupled. So let's try and measure from the input here to the coupled. And here we see something completely different. Of course, this is a resonant problem, and this is due to the length of this. And anyway, this is made for 900 to 1.3, and this is 1.3. And you see, we got about 6 dB. And if I move down to 900, See, we still got the 6 dB. So this is only this tiny little bit of it where it is the 6 dB coupling. So this is the linear Rf detector, and it says the frequency range where this is accurate, 900 to 1300. So what I did is I changed the span here from 900 to 1300, and now I'm just using the tracking generator as a signal generator for the measurements here, and then I put in my DC voltmeter and measured the DC volt output, and I got 0.2. Oh, sorry, I'm not able to hold everything here at the same time. But anyway, I get DC output. So this is very useful for detecting RF levels. I still haven't figured out what is inside this one. I don't measure anything at all, but I believe maybe this is a DC voltage, either enable or disable circuit for the RF. So this is like a pulse modulator or something like that. Also, I'm a little bit curious about what is inside this one. I don't know how to open it really, or just it's probably gonna break. How do I open this one? That was really weird. So there's just an inductor in here. So it was soldered to this end and then pressed through here, and somehow they managed to put it back in here. I can't use that for anything at all. But an inductor? Really? So this is of course to kill the HF signals. There's probably a little bit of HF still on this. So what the heck is inside this one then? This is really funny. This one was not soldered or anything. I think they cut this end to exactly the right length. So there's a tiny little bit of capacitive coupling between this one and the sensor pin. So, and I believe I measured 50 dB. So there's a 50 dB attenuation to that point. And then you get almost all of it through here and just a tiny little bit out here. So that is what it does. Yes, correct. All of it goes straight through. Let's try and put it back on this connector. Now is what I'm doing. The tracking generator goes straight through this unit, and I put in a little load on the other side, and now I'm measuring what is the coupling to the output. And believe it, yeah or not, it's 50 dB, and it's really flat. In this 900 to 1300, let's just span a lot more, right? Let's start from 0, and then let's stop 3 gigahertz. Isn't that amazing? Of course, at lower frequencies, the capacity in there, the coupling will be a little bit low, right? But when you get up to a certain point, it's going to be more and more flat. Well, 50 and then 40 anyway. But it's not walking around completely crazy. So let's look inside the attenuator. I had the idea this one could be rotated for adjustments, but it just don't look like that, right? Look at those two, and they'll fit those 2 screws. Maybe I can loosen these 2 and rotate it a little bit. I don't know if there's an oval hole here or anything. See some handwritten stuff as well. I believe we can take out the whole attenuator assembly from this mounting plate. But I'm starting to open it here from the back. I don't know exactly where to open it. So this is the internal parts of the attenuator. So look at the output here. So there's a coaxial connection to the inner part here, because this is of course rotating. So this is the slider that goes on the carbon film, but this carbon film is actually also a transmission line at the same time. So this is the input. Look at the input transmission line, and then it goes in here where the slider is. So at this very point here, we got no attenuation because we are very close. And then there is a coupling here with this golden tube, I guess. This is located here. Ah, this is the ground. Okay, this is the ground connection, and there's also some electrical padding and stuff like that. So this one is here because this part rotates. Okay, and they want good grounding here, so they, okay. Anyway, I hope I can assemble this again, because I think this little tube here is actually loose. See, if I touch this, so it's going to stay in here, and hopefully I can make it stay in here when I assemble this again. And there's a little springy part here. See, this we don't want to lose as well. Ooh, how difficult. I was about to lose my mind. But that is the classical thing with RF stuff. So this is a little flexible gasket. It's actually supposed to go in here and stay there. And then those two parts could be moved from here, and here they're loose. See, there's actually another little slider out here, and it slides here, so this needs to be lying flat. Whoa, this is some funky stuff, huh? That was something. Oh, it is assembled again, and now it works, and it's nice and flat and good again. But it was difficult to get all the parts and make them stay, and hold this and hold that, and don't fall down there and whatnot. So now I have shown you what is inside one of them, so you don't need to open it yourself, alright? Please don't do that. It is nearly impossible to, assemble correctly again. But I did it because I am super patient. Or not. One last thing to wrap this up. This is the RF output connector, attenuator, and that attenuator is 10 dB. That's quite flat, but alright, it's not a 20 gigahertz attenuator or anything, but let's see. Marker, if I crank it all the way up to the first dB error is 1.6 gigahertz for the first 1 dB. And if we continue for 2 dB error, let me see. Nah. 1.4 dB error at 3.2 gigahertz.